Class, welcome to the lecture number 16th of the course, Power Station Practice. So, in the first part of this lecture, I am selecting a very simple theoretical topic, and the topic is means how will you select the number of generating units in a power station? Means selection of number of generators and size. What do you mean by size? By size I mean rating or capacity. Selection of number of generators and size of generator. So this topic is also called as the choice of size and number of generating units. So basically what factors determine the number of generating units, how many generators you should means install in a power station, and what should be the capacity of the generator. So it depends upon certain factors. Okay, so which I have already prepared here, and I will try to explain them one by one. So economics of generation. Economics of generation means it depends a major part or I'm saying a major concern of the economics of generation is the selection of number of generator units and the size of the generators. Okay, so because and how will you decide the number of generators, how many generators there should be, and what should be the size of the generator? Basically it depends upon your demand. Okay, first you should know what is your load demand. Okay, depending upon your load demand, you will determine the capacity of your power station, and depending upon the capacity of the power station, and you will determine what should be the size of the generators. Okay, and how many generators you should install. Okay, so most important thing is load data. So if you have a load data, with the help of load data, you can draw this data, load data, in the form of a curve which is called as load curve. So once you have this load curve, after analyzing this load curve, you will determine the number of generators and size of generator or generators, because it is not necessary that you will use all the generators of same capacity. You can use some generators of higher capacity, and you can use certain generators of lower capacity depending upon the load curve. Means it should be such, if it is like this, if your load curve is like this. Okay, I'm saying this is your monthly load curve. So you can see that this peak load, it occurs for a very short duration of time. So what happens, you have to see, if you will use a single generator of large capacity equal to the maximum demand, so you will see that generator is to be kept on at its rated value for a very small period of the time. However, for the majority of the time, this is the majority of the time, for the majority of the time, this generator will operate at its capacity below 50%. Means if X is the capacity of the this generator, then for majority of the time this generator is operating at 0.5x. Okay, so it is not economical. So what we have to do, we will select certain number of generators, or we will say that okay, this is the base load. For this base load, this load will be supplied by generator number 1. Then we have this intermediate loads, 2 intermediate loads. This will be supplied by generator number 2. This load will be supplied by generator number 3, and this peak load will be supplied by generator number 4. Okay, means we have to turn on this generator number 4 for a very short duration of time. Then this generator number 3, it is also to be kept on for some duration of time. Same is case with the generator number 2. However, generator number 1, it is to be kept on all the time. Okay. So once you have the load curve, then only you can decide the number of generator units or number of generators and the size of the generators. So let us see what are the factors that determine the number of generating units and their operating schedules. Okay. So the first is we are saying that means suppose I have 4 generators here. I am saying I have 4 generators. The capacity of these 4 generators means summation of the capacities, capacity of this generator plus capacity of this generator plus capacity of generator 3 plus capacity of generator 4. So if I will take the addition of all the capacities, it should be means these capacities should be able to satisfy the peak demand. Okay, that is what I have written here. The total capacity of the generating units should be capable of meeting the peak demand of the power station. Okay. The second point is that machines, suppose we have generators are also machines. I am saying that these machines operate at maximum efficiency at 75% of their rated capacity. Suppose I am saying it's the capacity of the generator 1 is, suppose it is 150 megawatt or 100 megawatt. So it will operate at its maximum efficiency at 75 megawatt. Okay, means 3/4 of its capacity. Okay, so I am saying here machine operates with maximum efficiency at 3/4 of the rated capacity. 3/4 means 75% of the rated capacity. So the number and sizes of the units must be so selected that they operate at maximum efficiency and better overall efficiency. So means all the generators, they should be number of generators should be selected in such a manner that all the generators should operate at 75% of their rated capacity. Only then the overall efficiency can be achieved. Okay, so why are we talking about efficiency, not maximum power transfer? Okay, so because in case of electrical engineering we talk about efficiency, we don't talk about maximum power transfer. However, in case of electronics engineering, they talk about the maximum power, because even if maximum power transfer occurs, then only we will be able to supply only the 50% of the rated power, 50% of the power under maximum power transfer condition. Okay, so that is why we know that even if we somehow fulfill this maximum power transfer condition, then even then we will be able to supply only 50% of the power. Got it? So that is why we talk about efficiency only in electrical engineering. So I am saying that the generators should be the number of generators should be selected in such a manner that each generator is loaded to 75% of its rated capacity, so that better overall efficiency is achieved. Okay. Then comes the important one more important factor or feature, that is called the reliability of the service. What do you mean by reliability? By reliability I mean continuity of power supply. Continuity of power supply. Got it? So reliability of the service is important. There should be a spare set of capacity of the largest unit in the power system, so that maintenance and repair of the working units may be carried out without any disturbance in power. So what we do, suppose we are saying that, let me take another page. So that I can write it clearly. Okay, yeah, here. I am saying that I have 4 units. Okay. Out of these 4 units, suppose I am saying that unit third, it is I have 4 units. 4 number of units, I am saying number of units 4. And third unit is of largest capacity. I am not saying taking the example of the previous curve which I have shown here. I am not taking this 1, 2, 3, 4, these 4. I am taking these 4. I am saying randomly I have 4 units, 4 generators, and out of the 4 generators, third unit it has the largest capacity. Okay, it has the largest capacity. So what we do, so we want the system to be reliable. So what we do, we are, instead of 4 units, we will use 5 units. Okay, and these 4th unit, and we will add one more extra unit, that is the 5th unit, and the capacity of the 5th unit should be equal to that of the 3rd unit. Okay, means this is the largest unit, so we need one more unit of this capacity of the largest capacity, so that if we want any maintenance in the system, we want to maintain any other generator, we can take out these generators and the supply can still be maintained. So suppose that there is some fault in this generator number 3, what will happen? There will be disruption in the power supply. So what we do, we will keep one spare unit of the same capacity as that of the capacity of unit number 3rd, so that even if there is some fault in unit number 3rd, that spare unit of capacity equal to the capacity of unit number 3rd, that can be put into service. Okay, so this is called as reliability. So one more thing, so if we are designing the power hose, I told you that the gestation period of a means power plant, it is around 5 to 7 years. Okay, so once you are designing it, means if you need some power after 7 years, means in 2029 you will start constructing your plant in 2022. Okay, but while constructing the plant while constructing the plant in 2022, okay, consider in mind that when this plant will be considered in 2029, it should cater the future needs for up to 2035, means आगे का 7 साल का और सोच के चलना है आपने, ठीक है. So that is called as future demand growth should be considered. Last 4th point, future demand growth should be considered. Got it? So then comes that whenever we are designing a power this power station or this power hose, so what we do, if we are designing it, we are saying that the expected load is 100 megawatt. Okay, so we will design the power this power hose for 115 or 120 megawatt. Means we will take an excess margin of 15 to 20%. So that's what I am writing here. Capacity of the station should be 15 or 20% more than the expected maximum demand. So these are the factors which will decide the number of generating units. Okay, I'm not saying about the size of the generating unit, I'm saying about the number of the generating units or the number of generators. So these 5 points. So next, let us see. I am saying that if minimum how many generators you need in a power house, minimum you need 1, maximum you can use up to any number. Okay, but minimum there should be at least 1 generator in a power house. Only then it will be called as a power house. If there are no generator in a power house, what will you generate? Nothing. Okay, so minimum there should be 1 unit or 1 generator. So if you are saying that minimum there should be 1 generator, and you are saying that the capacity of that single generator, it should be equal to the maximum demand. Okay, so what will happen if you are using a single generator of capacity equal to the maximum demand, what will happen? It will have certain advantages and disadvantages. So what are the advantages? Suppose I am using a single large unit. I am using a large unit of a large size unit. I am using a single large size unit. It will have advantages. What are the advantages? Means cost, investment cost or initial cost. Initial cost will be low. Why? Because you know that if I'm for 100 megawatt, if I am using 1 generator of 100 megawatt, and on the other hand, if I am using 4 generators of 25 megawatt, obviously these 4 generators, they will means the cost of the 4 generators will be more as compared to the cost of the 100 megawatt generator. Why? Because when you are considering more number of generators, means more material is required, more labor is required. Okay, so that is why the cost increases. So that is what it is written here, that is large size units have lower capital cost. Okay, lower capital cost per kilowatt. Okay, if obviously 1 generator, it will require less space. 4 generators, it will require more space, means more floor area. If we have single generator, we need lesser labor, and operating and maintenance cost is lower. And if I am using 4 generators, then operating and maintenance cost is higher. And obviously if I am using a single generator, it will have better efficiency. So that is what it is written here. Large size units have lower capital cost per kilowatt, needs less floor area, requires lesser operating labor, and have better efficiency. So therefore we can conclude that large size units are economical both from the point of view of initial investment and operating cost. Means if we are using a large generators or large size generators, its initial investment will be low, and moreover its operating cost will also be low. So but using a single generator of large capacity, it will have certain of large capacity equal to the maximum demand, it will have certain drawbacks. What are the drawbacks? Let's see. So I will show here. Yes, I will take again this example of this curve. I will write again here. What are the drawbacks? Okay, so this is my 24-hour data. This is time 24. So this is maximum demand, and I am saying this is the peak demand. I am using a single generator of capacity equal to the maximum demand. So for how much time this generator is operating at its maximum demand? Only for few hours, 2 hours a day. And for the majority of the time, so this is, so I am saying 12 hours is here. So this is power, this is half of the power. And for majority of the time, it is operating at a capacity which is less than the 50% of its rated capacity. Okay, so means what I am doing means I am wasting money here. I am burning more fuel and I am getting lesser output. Okay, so that is what here it is saying, that load on the station varies throughout the day. Okay, there are times when load on the system is much lower than the peak load. Okay, during these times means when load is less than the peak load, it is called as light load periods, when the load on a system is very low, or when the load on the system is below 50% of its rated capacity. So during these periods, the efficiency of the machine will be low, because machine operates at maximum efficiency when it is loaded to at 75% of its rated capacity. So I am saying by using a single unit of large capacity at a load which is less than 50% of its capacity, it reduces the efficiency. And if the efficiency reduces, what will happen? The cost per kilowatt will increase. Okay, so the cost of generation will go up. Got it? So moreover in case, suppose there is fault in this generator, what will happen? The power supply will be interrupted. So what will you do to overcome this problem, or to increase the reliability? You need one more generator of the same capacity equal to the maximum demand, so which will increase the cost further. So that is why we say that using a single generator equal to the maximum demand or peak demand is not a advisable solution. Okay, got it? So then we say that to overcome this problem, size and number of generator units may be selected so as to fit the load curve as closely as possible. Okay, then each unit can be made to operate in such a way that it operates at a load to give maximum efficiency, means at 75% of its rated capacity. So also the reserve required would be only that of the one unit of the largest size chosen. So I've told you, means if you have 4 units and third unit is the largest, in that case you need only one reserve unit equal to whose capacity is equal to the capacity of the largest unit. Okay. So this way we can we can increase the reliability, we can reduce the cost. Okay. So the disadvantages of large number of smaller units are, so but what happens if we are using a large number of smaller units? Means more floor area is required, initial cost per kilowatt would go high. Okay, maintenance would be more. Okay, and you need more this more technical staff for maintenance of these more machines. Got it? So I am saying that the number of units, they should not be size of the unit should not be very large, and it should not be very small. Okay, as such the size of the unit for a power station has to be compatible with the total capacity of the power station. Okay, means but the number of units and size of the unit should be such that it should means that the capacity of the plant should be equal to the maximum demand or maximum load or peak load. Got it? So this was a small topic, a theoretical topic, how you select the number of generating units and size of the generating unit. So next, let us discuss one important this topic, which is called as power factor. I think I have to use this. So let us come to another topic that is called as power factor. You all know very well what is power factor. Okay, what is power factor? You all know very well because you have studied it in your previous means semester. What is power factor? Let me take some spare pages as well. Okay. So what is power factor? Suppose for explaining the power factor, I should again repeat what is resistive load, what is inductive load, and what is capacitive load. Okay. So then only you will be able to understand what is concept of power factor, what is power factor. Okay. So first I will say, let us assume that I have a resistive load, purely resistive load. Should not go off screen at any period of time. I should not go off screen because it is a very important topic. So okay, yeah, it is right now. So I am saying, suppose I have a purely resistive load here, okay, R, and I have some sinusoidal source here, V, and some current is flowing in the resistor I. Okay, so for a sinusoidal voltage wave shape, this is a sinusoidal, means purely sinusoidal sine wave. How will the current behave in a resistive load? So I will show it in a in the form of wave here. So this is my time t, and I am saying that this is my voltage V. I am drawing it very slowly. Okay. So I am saying this is my voltage V. Got it? What is this? This is my voltage waveform V. So this is a resistive load. So what will happen to the current? The current will be in phase with the resistor. What do you mean by current will be in phase with the resistor? That when the voltage is 0, current will be 0. Okay, and when the voltage is at positive maxima, the current will be at its positive maxima, and the voltage is when the voltage is at its negative maxima, the current will again be at its negative maxima. So the current will be like this. The current graph will go like this: 0, then maximum value, then here, again here, then here. Okay, so this is what is this? This is current I. Okay, so you can see that the current and voltage, they are in phase because both are starting from 0 at the same time and both are ending at 0 at the same time. When the voltage is at its positive maxima, the current is also at its positive maxima, and when the voltage is at its negative maxima, the current is also at its negative maxima. Got it? So this is for purely resistive load. I am saying current and voltage are in phase. So voltage and current are in phase. Got it? So next let us see this purely inductive load. I am taking pure cases. Okay, purely inductive. Purely inductive load means the resistance of the wire here is 0. Okay. What it? Here I have current R, here I have inductor L, and here I have voltage V. So again for a sinusoidal voltage wave shape, ठीक है ना? The current will behave like, I will draw it here. So I am saying this is my voltage V. Okay, this is my voltage V. So this is a purely inductive load. The current will start 90 degree later. Okay, so the current will go like this. Okay, so this is my voltage V and this is my current I. So you know that I crosses this voltage I. This is the current wave I. So you know that I crosses 0 value after some time. Okay, when the voltage has reached to its maximum value. Okay, since the current starts from 0 to positive region. Current starts entering from 0 to positive region. Okay, after some time, means पहले voltage positive जाएगा, उसके कुछ time के बाद current positive जाएगा. So that is why we say that current lags the voltage. So current lags voltage. So that is why, because of lag, that is called as lag network. Got it? Now third case, I will take the case of a purely capacitive. purely capacitive load. Purely capacitive voltage source V, sinusoidal current I. So how the circuit will behave? The circuit will behave like this. This is my V. So what will be current? Current will be like this. Okay. So you can see here, this is voltage V and this is current I. When the voltage is 0, there is some value of current in the system, okay, which is nothing but the maximum value of the current. So you can see this I leads V. That is why they are called as lead networks. Got it? It is clear. So let us let us draw the power waveform of all the three circuits. So you know that power is nothing but V multiplied by I. Okay, so this P is nothing but average power, average value of the power. How will you calculate the average value? I will show you. So I am saying this was the curve like this. I will again draw the curve here. Okay, so I am saying in this region means voltage when voltage is positive and current is positive. Okay, so if voltage positive, current positive, what will happen? Product will be positive, positive multiplied by positive, positive. Okay, so let me draw again this waveform. So this is my voltage. Okay, and this is my current. I will draw current in a dotted form. Okay, so when voltage is positive, current is in the dotted form and voltage is in the solid form. So when voltage and current both are positive, power will be positive, because power is nothing but V into I. It will be like this. We call power curve. And when voltage is negative and current is negative, negative multiplied by negative, again positive. So again the power will come out as positive. Okay, so this is the power curve. Power is equal to VI. Got it? So if I will take the average value of the power, so the power is like this. The power is like this. The average value of the power, I will show it on another page. I am saying this like here. I will take another page here. Okay, I am saying this is my power. Okay, so what will be the average value? Average value will be around somewhere around here. This will be my P average. Okay, so I got the average value of the power. I have shown you here, P average power. This power is nothing but P is equal to V into I, and this is the average power. Average power, it comes up to this point here. If I will take the second cycle, it will go here. So this is average power, this power. This area under this curve, it is my average power. Got it? So let us draw the power for the second circuit now. So if you will see here, I will draw it here again. I will draw it here again. This is my voltage. My voltage, and I will draw the current in the dotted form. Let me draw the first 90-degree angles somewhere in the middle. So I will draw the current in the dotted form as like this. So this is my current. Okay, so let us if you will see here, you will get 4 curves. Okay, so first part, when this region, this part, from this part here to here. Okay, in this region you can see that voltage and current, voltage is positive, current is negative. Voltage positive, current negative. So positive multiplied by negative will be negative. So this is for purely resistive load. I am drawing now for inductive load. Inductive load time. So first is this, suppose I am saying this much time, this I am saying it is this time. Okay, so current negative, voltage positive, positive multiplied by negative, negative. So the power will go like this. Power will go like this. Like this. Okay, then from this point to this point, okay, this point to this point means this much time, both voltage and current, they are positive. So what will happen to this power will be positive again. So I'm saying it is this much time, so power will be positive here. Got it? Now from this point to this point, okay, current is positive but voltage is negative. So positive multiplied by negative, negative. So I'm saying it is this much, again negative. And from this time to this time, both current and voltage are negative, so power will be positive. So I'm saying it is this much. So you can say here we have 4 cycles, 2 positive and 2 negative. For one cycle of the voltage we have, and one cycle of the current we have 2 cycles of power. However, in case of a purely resistive node, we have only 1 cycle of power. Got it? So this is nothing but average power, which is given by P. This is the actual power, P is equal to VI. Okay, so what will be the average power? You know, this area is equal to this area and this area is equal to this area. All the 4 areas are equal. Why? Because the phase difference between the voltage and the current, it is 90 degree. Why 90 degree? Because of a purely inductive load. So average power will be what here? Average will be equal to 0. Similarly, for a purely capacitive load, if I will draw it here, so I am drawing again it here because I am showing the power on another page. It doesn't make any sense. Okay. So okay, I am saying that during this period, this to this period, first 90 degree, current is positive, voltage is positive, so power will be positive. So I will show it here. So this voltage positive, current positive, power will be positive. Now from this point to this point, 90 to 180 degree, current is negative, voltage is positive, so power will be negative. So 180 degree. From 180 to 270 degree, both voltage and current, they both are negative. So if they both are negative, negative multiplied by negative, positive, because power is nothing but the product of voltage and current. So it will be again positive like this. Hope it is in the frame. Okay. Again, during the last part, we see that current is going positive but voltage is negative. Current is positive, voltage is negative, so power will be negative. Got it? So again, this area equal, this area equal. Okay. So average power will be equal to 0 and instantaneous power will be P is equal to V into I. So you got. So you can see this both. This is for inductive, purely inductive. This is for capacitive, purely capacitive. So you can see that both inductive and capacitive circuit will give 0 average power, and only resistive circuit will give some finite power. Got it? And moreover, if you analyze these two curves, what will happen? You can see here power is negative, here power is positive. So I am saying the purely means these two waveforms, that the power waveform of a purely inductor and a power waveform of a purely capacitor, they are 180 degree out of phase with each other. Means these power curves of waveforms, these power curves of waveforms are 180 degree out of phase with each other. Okay, because when the power is going negative here, the power is going positive here. Got it? And the average power in both the curves is equal to 0. So am I done so far? Any problem so far? Hope there is no problem. Okay, so this was the case of a purely inductive, purely capacitive and purely resistive load. So in case of a purely resistive load, we have some finite power. However, in case of a purely inductive and purely capacitive load, the average powers will be equal to 0. Okay, and though there will be some instantaneous power, but average power will be equal to 0. And the power waveforms of a purely inductive and a purely capacitive circuits, these power waveforms, what will happen to these power waveforms? They will be 180 degree out of phase with each other. Okay, so let us take case of this what we say this RL load. Okay, now we will take a case of RL load. So what is RL load? We have a resistor and we have an inductor. This is L, this is R, and we have a voltage source here V, and some current is flowing in the circuit I. So let me draw the voltage and current waveform here. T. So I'm saying this is voltage waveform, sinusoidal. I have a sinusoidal voltage waveform here. Okay. So since it is an inductive circuit, it is an RL circuit. It is not neither a purely inductive nor a purely resistive circuit. So because of this inductor, the current will lag, but it will not lag by 90 degrees. So this was 90 degree, this was 270 degree. The current will lag by some degree, but not 90 degrees. So this is my current waveform. So this was my voltage V, and this is my current I. Okay, you got it? I'm saying it is not 90 degree out of phase, but there is some phase difference between the voltage and the current. And what is the phase difference? So this is the phase difference. Suppose I'm saying this, I am denoting this phase difference by phi. Got it? So let me draw the power curve. Okay, let me draw the power curve for this now means yes, let us draw the power curve. Okay, I will try to draw the power curve here. Let me see if I have a red pen here so that I can differentiate the power. Yes, I have the red pen here, so it will be easy for me to demonstrate now. Let us demonstrate now power. So from this 0 to 5, you can see voltage is positive but current is negative. What will happen to power? The power will be the product of 2 and it will be negative like this. Okay, got it? So now from, you can see up to this point, voltage is positive, current is positive, so power will be positive. The power curve will go like this. I am saying it will go up to this point here. The power is going like this and it is coming out like here. Okay, because up to this time both voltage and current, they are positive. Now after this time, you can see the voltage is negative but still the current is positive. So up to this time, voltage is negative, current is positive. So product of positive into negative will be again negative. So current power will go like this. Okay. Now after beyond this point, from this point onwards, you can see the voltage is negative and the current is also negative. Okay. So if both are negative, negative multiplied by negative will be positive. So the power, the curve will go like this again. Got it? And then again negative in this region. Okay. So this is the dotted area, shaded area. This negative region, I am shading this region. Okay. And this is the positive area. Okay. So I am saying this negative portion, so I'm let's write P is equal to VI. I'm saying this P. I'm saying what will be the P average? P average will be like here, somewhere here. Means this area plus this area plus this area plus this area plus this area. So this negative area is small, positive area is more. So overall the average power will be positive. So this will be P average. So this P average is the active power that actually goes into the load. What is P average? P average is the actual power. Let me use the blue and black pen. Actual power that actually goes into load. What is negative portion? Negative portion, which is shown by shaded, negative or shaded portion, is power that is sent back to the source. source and is called reactive power. And is called reactive power. This negative shaded area, it is the negative power, and this power is sent back to the source, and this power is called as the reactive power. Okay, got it? So suppose what happens, I am saying suppose if the power factor is degrading, means it is phi. If phi is increasing, what will happen? If phi will increase, what will happen? This curve, this P is equal to VI curve, it will start shifting downwards. Got it? This curve will start shifting downwards and the negative area will increase. Got it? Suppose I am saying, suppose that I have this RL circuit. Suppose I am saying in this RL circuit R is equal to 0. So if R is equal to 0, in this RL circuit I am showing if R is equal to 0 to demonstrate if power factor increases, this curve will shift downwards. I am demonstrating it here. So I am saying if R is equal to 0, that is if R is equal to 0 in RL circuit. In RL circuit, if R is equal to 0, what will happen? Let me draw the power curve for this. I am saying this is time t. So the curve for the inductive load, it was like this. Power curve was like this. Okay, the power curve was like this. Got it? Wasn't it like this? So I am saying as R increases, I am saying if R is equal to 0, the power circuit will be like this. So I am saying when R increases, what will happen? When R increases from 0 value, okay, what will happen? This power curve, it will shift up, power curve will shift up, power curve will shift up from 0 value. Why from 0 value? Because if it is if R is equal to 0, then it will be purely inductive. This area will be equal to this area will be equal to this area, and average power will be equal to 0. Okay, so I am saying if R increases from 0 value, power curve will shift up. So this whole curve, time line is here, this will shift upwards. So if the power curve shifts up from the 0 value, okay, na? So I am saying say to 0.1. Okay, say to 0.1 means what I am saying, the power curve will shift up, say to 0.1. I am saying now the curve will become like this. So it will become like this. Here you can see the negative area is less and the positive area is more here. Okay, so if I will try to show it here, how will I show it? I will show it like here in this graph. I will show it like say 2.1 means suppose this is 0.1. If further I will increase R, what will happen? The curve will start increasing more to upwards. If the curve will start increasing more upwards, so average area will further increase. Sorry, means this positive area will further increase and the power will further increase. So I will say that the power will increase and suppose the new average power will come to somewhere this point. This is called as point number 2. Okay, and when I am saying this, if the resistor increases to such a high value to a very high value such that the effect of inductor is negligible. If the effect of the inductor is negligible, what will happen? I will take here. I am saying if R increases to such a high value that the effect of the inductor becomes negligible, so this curve will look like this. So the curve will look like this. This is time. So the curve will look like this. So what will be the P average? P average will be here, this, and it will be positive. Because this area is this is 0, this is positive region, this is negative region. So this area, whole area is positive now. So average power is coming here. So this will be the average power now. Got it? This is average power and this is P is equal to V into I. So what I have concluded, what are my remarks? I will conclude it with the remarks. I will conclude it with a remark that is average power is maximum for a purely resistive load. Average power maximum for purely resistive load. And second point is that for an RL and RC loads, they have some portion of power curves which are going negative. They have some portions of power curves which are going negative. Okay, like here. Hence, their average values will be lesser than that of a purely resistive load. Okay, so power factor, I can say what is power factor? I can say power factor is nothing. Power factor is nothing. But it is a measure of the degree to which any given load matches that of the pure resistive load, pure resistance. So power factor, it can be 1 for a purely resistive load, it can be 0 for a purely inductive or capacitive load, and it can be between 0 and 1 for purely inductive and purely capacitive load for an RL and RC load. But for an RL load it will be lagging, and for an RC load it will be leading, because in case of a RC load the voltage was leading, the current was leading the voltage. Okay, so I am saying power factor is nothing but the degree to which any given load matches the resistive load. Okay, got it? So I am saying power factor is nothing but it is the degree to which any given load matches that of the purely resistive load. So I am saying P load, any load divided by PR, means ये जो load है इसका सिर्फ resistive part जो होगा. Okay, I am saying if power factor is equal to 1, कब 1 होगा? When P load will be equal to PR, and power factor will be equal to 0 when P load will be equal to 0, or when power factor will, I am writing it was when power factor will be equal to 1, P load will be equal to PR, and when power factor will be equal to 0, P load will be equal to 0. So what is P load? P load is nothing but average power of any given load. Okay, and what is PR? PR is the average power of a resistive load for same voltage and current magnitude. Got it? So what I am saying here? I am saying power factor is nothing but the degree to which the given load matches that of a pure resistive load. So power factor is indirectly a ratio of P load divided by PR. So when power factor is equal to 1, P load is equal to PR, and when power factor is equal to 0, P load is equal to 0. Okay. So what is P load? P load is the average power of any given load at certain voltage and current magnitude, and PR is nothing but average value of a resistive load for the same voltage and current magnitude as that of the P load. Okay, got it? So I will take 5 minutes more. I know it is going beyond 50 minutes, but I cannot skip this lecture because the concept cannot be delivered in 2 lectures. The concept has to be delivered in a single lecture. So let us see what is apparent power and power factor. Power and power factor. Okay, we know that V is nothing but Vm cos omega t plus theta V, and I is nothing but, this is V and this is I, because this is a sinusoid, so it is to be represented by small letters. is nothing but Im cos omega t plus theta I, where theta v is the voltage angle, theta is the current angle. They both have means the sinusoids, they both have their own angles. Okay, so what is average power? It will be Vm Im divided by 2 cos theta v minus theta I, and you know that Vrms is nothing but Vm by root 2. Similarly, Irms is nothing but Im by root 2. So P average will be Vrms into Irms into cos of theta v minus theta I, and the units are watts. Okay, what is Vrms and Irms? Vrms and Irms is nothing but the apparent power. Okay, so in case of a purely resistive load, you know that theta v minus theta I is equal to 0 for pure resistance or a purely resistive load. So for a purely resistive load, we say that P average will be equal to V RMS into I RMS. So I can say that for a purely resistive load, average power will be equal to the sum of the RMS voltage into RMS current. This average power is what we are consuming. This average power is equal to VRMS into IRMS means we are consuming whatever the means company is sending to us. Means we are consuming, this case when P average is equal to VRMS into IRMS, we are consuming whatever power company is sending us, because no power is sent back to the source. Okay, because if you will see the power curve of a purely resistive load, so it is always positive. Okay, positive means no power is sent back to the source. Whatever is coming from the source, we are consuming it. Okay, and its apparent power, which is equal to Vrms into Irms, the units are volt amperes of apparent power, and this cos of theta v minus theta I, it is the power factor. It is called as a power factor. So theta v minus theta I, it can be between plus 90 or it can be plus 90 or minus 90. Plus 90 for a purely capacitor and minus 90 for a purely inductor. Why minus 90? Because it is lagging, plus 90 because it is leading. Got it? Okay. So what is your average power? Vrms into I Rms into cos of theta v minus theta I, or average power is equal to Vrms into I Rms into power factor. So what is power factor? Power factor, I am saying nothing but the degree to which a given load matches to that of the purely resistive load. Okay, and I am showing here, so I am showing it if it is a purely inductive. Okay, the power will be like this. Average power will be 0. So as we go on increasing the resistance, the curve will start shifting upwards. Means time axis will be here, but this curve will start shifting upwards, and the average power will keep on increasing. So I think that is enough for today's lecture. In the next lecture, I will continue with one numerical, and then we will see what are the reasons for poor power factor and the methods of improvement of the power factor. So thank you very much. So one more lecture and unit, I will finish this unit number 2 as well. Thank you very much.